All right, 2019 number 2. All right, what do we got here? The velocity of a particle moving along the x-axis is given by the differential function via pt, which we have a chart for up here. It's measured in meters per hour, and t is measured in hours. Selected values are shown in the table above. Particle B is at the origin at time t equals 0, so that's what we see as the origin. Justify why there must be at least one time between 0.3 and 2.8 at which the derivative of this, which is velocity, so the derivative velocity would be acceleration, equals 0 meters per hour. So why is that the case? Well, if we just look at this from 0.3 to 2.9, what has to have happened here, right? So basically we're saying the derivative of these values, why would it have to equal 0 at some point in time? And let's think about what that is. The derivative is the slope of these from this point to this point. So somewhere in between here, the slope from here to here has to equal 0. Well, let's just kind of draw this out just real simply. Okay, at 0.3, I'm up here at 55. And then at some time later at 1.7, I'm down here at negative 29. And then some point later at 2.8, I'm back up to 55. And so in its simplest, this is going something like this, right? That's simplest. But they do tell us a couple things about this. They tell us that it's given by the differentiable function via p. So if it's differentiable, we can't get anything like this. So we must have some type of smooth thing like that, at least like that. Theoretically, it could be doing even more dips in this, right? It could be going like up and down, or down and up and down and up, and it could do it more, but at least it has to do something like this. Well, right at that location then, if that is in fact the minimum, we don't know that yet, we would have a tangent slope of 0. And this is, basically this is the extreme value theorem. Well, that we know that in order to get a slope of 0, we must have a min or a max somewhere, we must have a min somewhere, and we know that it's differentiable, so whenever that min occurs, we don't know for sure that's 1.7, but it's potentially 1, then it would have to have a 0 slope. The other thing that you could do, even if you didn't know about this point in the middle, if you just had these two beginning points, well, what's simply the average slope between those 2 points, or the mean slope? So if you did the mean value theorem, says, hey, if your average slope between 2 points is, whatever, in this case it's 0, then somewhere in between there it has to take on that slope. So if we were to actually say okay, we have point via p of 2.8 minus via p of 0.3, and put that over 2.8 minus 0.3. Just ignore that point in the middle for now. And what is v of 2.8? Well, it's 55. And so is v of 0.3. And so then we would have 2.8 minus 0.3. So 55, it doesn't matter what's on the bottom. The point is we end up with 0. So since the mean or average slope is 0, and we know this thing is continuous because they already told us it's differentiable, then somewhere along there has to be a slope of 0. Somewhere between 2.8 and, oops, I wrote this wrong. Somewhere between 0.3 and 2.8, therefore there must be a slope of 0. And that's basically the mean value theorem. Like I said, you could also talk about it as the extreme value theorem because there's a max or a min. Whatever makes the most sense to you. The point is, we know somewhere there has to be a slope of 0. Okay, let's move on to part B. Just erase all that. So part B now says, use a trapezoidal sum with 3 subintervals, 0 to 0.3, 0.3 to 1.7, 1.7 to 2.8, to approximate the value of 0 to 2.8. Okay, remember, so it is saying just these 3 intervals, so this is very important. I'll do this in blue. They only care about, I'll draw these as trapezoids. These 3 trapezoids, okay? For this problem, for whatever reason, they don't care about this last part. Okay, and we're just approximating that value using a trapezoidal sum. I think the easiest way to do that is just do 3 trapezoids and add them together. So the first trapezoid, if you think about remember this is like the delta x, or the change in x, and if you remember the formula that we used, it was delta x over 2 times plus f of b. So we're just going to basically use that 3 times. And again, just so you guys can kind of recall, that's really just from the actual formula for a trapezoid, which is this. That's the old area formula for a trapezoid. So that's where that comes from. We just use a little bit different language because it's delta x instead of h, because it's literally the change in x. That's like our height of a trapezoid. And then these are like our 2 heights, your base 1, your base 2. So what's the first one going to be? Well, the first delta x is from 0 to 0.3, so it's 0.3. Divide that by 2. Your first f value is 0. Your second one is 55. All right, what's the next trapezoid? The next trapezoid is 1.7, from 0.3 to 1.7. So if we just did 1.7 minus 0.3, we'd get 1.4. Divide that by 2, and now it'd be 55 plus a negative 29. Okay, and the next one is one from 1.7 to 2.8. 2.8 minus 1.7 is 1.1. Divide that by 2. And then that would be negative 29 plus 55. And I'm just gonna find these and add them all up. So I'm gonna do that on the calculator. You could do it on the calculator too, but that's how I would do it from here. So what do I get here? So when I plugged in my calculator, I got 8.25, 18.2, and 14.3. Again, we're just adding it all up because it's just a trapezoidal sum. And so that means that this integral is approximately 40.75 if you use TRAM, or trapezoidal approximation. All right, let's go to the next one. All right, part C. It says a second particle Q also moves along the x-axis, so the velocity for this thing is given by an actual function now. This looks like a pretty complicated function, but remember, we are able to use a calculator in this question, so it shouldn't be too bad. So here's a velocity, meters per hour. Find the time interval during which the velocity of particle Q is at least 60 meters per hour. Find the distance traveled by particle Q during the interval when the velocity of particle Q is at least 60 meters per hour. Okay, so the first thing we need to find out is, when is this thing greater than 60? Okay, so for this problem, you can hear my son kind of crying in the background. Say hi, JJ. So for this problem, what I did is I just put the actual equations in the calculator. I put the first equation they gave us, the velocity equation, in y1, and then I just put the second equation, which is just 60, in y2. And I'll show you what I did to my window. I set my x values from 0 to 4 because we know that they only give us the 0 to 4 interval. And then I set my y values from 50 to 100 because remember, we only care about what happens after 60. So I did 50 just so we could see a little bit after 50, and I did 100 because I figured it'll probably ain't going past 100, but who knows, maybe it does. And then if I hit the graph, here's what I get. I get that. It looks kind of like a parabola. It's not. It's a cosine curve. And I get a line. And so basically, I'm trying to figure out what's happening. When does it cross over 60 there, and when does it come back down? Well, the calculator has the ability to do that. Remember, I can hit second calc, and I'm going to go down to intersect. And so it just asks me for what's the first curve. And the first curve is the cosine curve. Second curve is the flat line. And then it says guess. And this doesn't really matter, but you just want to kind of be close to where the intersection is. Boom. Okay, 1.866. Let's write that down. We do the same thing again to calculate the second intersection. So now, first curve, still the cosine curve. I'm just trying to get over closer to where the intersection is because I'm going to have to guess. Second curve is still the 60 line. Josh was very excited about this problem. And now we get 3.519. All right, well, so now that we have these values, right? These are the time interval during which the velocity of the particle q is at least 60 meters per hour. We found that it's between 1.866 and 3.519. Now we want to find the total distance traveled. Okay, we could find the total distance by, remember, the total distance is simply the integral or the antiderivative of velocity from a point to a point. So essentially it would look something like this. It would be from 1.866 to 3.519. And total distance, usually you actually want to use the absolute value. And this one, it won't actually matter, but you just want to get in the habit of using that. Of the velocity of q's function. Now that looks kind of complicated and maybe it's a lot of work, but actually it's really easy because that's already, this function is already in our calculator. So we could just plug all this into the FNINT function in the calculator. Let me show you how to do that real quick. All right, so remember we already have the function in your y equals, and it's just the y1 that we care about. And I've already done it, but let's just do it again. So I would say you go to math and you go to the FNINT function, boom. First thing you want to do is put in the function, but remember we technically want the absolute value. So I'm gonna hit math, number, absolute value, then I'm gonna go to vars, over to yvars, function, select the y1 function. Okay, there's the first thing that I want is the function inside absolute values. Then comma, then what's the variable? The independent variable. In our equation, it's t. On the calculator, I didn't bother changing it to a t. I just left it as x. Then your two limits, which was 1.866, and then comma your other limit, which is 3.519. All right, and then just let the calculator do the work for you. And so we get 106.109. I'm going to write that down. We get 106.109. So essentially our little integral here equals 106.109. Remember, this rate was in meters per hour, so this distance must be 106.109 meters, because this is a distance. Remember, when you take the antiderivative of a rate function, you get the total distance. So there we go. All right, let's go on to part D. All right, at time t equals 0, particle q is a position x equals -90. Okay, so we know the position of the starting position of particle q. Using the rule from part B, where remember in part B we were talking about not q, we were talking about p. They want us to know the total distance and the function of EQ from part C. Approximate the distance between particles P and Q at that specific time. Okay, so basically these two particles are moving. One of them we have this table for, one of them we have this function for, and at 2.8, where are they and how far apart are they? Simple enough. If you think about that, what that really means is kind of the distance between them could be represented like this. X of Q at 2.8 minus, and X is our position function, X of P at 2.8. And then because we don't really know which one's greater, we would just do absolute value here because that'll just give us the exact distance. That's what absolute value does. It gives us distance. Okay, well, do we really know these two things? Well, one of them we do kind of know already. It's here. This one is the position of particle P at 2.8. And really, that's what this would be because the starting position was 0. And this is the total distance it's traveled because it was the integral to 40.75. So actually, this is probably its position or a very good estimate of its position. So we could say this is approximately X position of particle P at 2.8. So now we just need to find this part. What's the position of particle Q at 2.8? Well, that shouldn't be that hard to determine either because if we were to write an integral out let's go from 0 to 2.8, we're using 0 because they gave us this information about this at 0 of x, at velocity, because they give us the velocity function. Wouldn't this equal position, because it's fundamental theorem of calculus, particle Q at 2.8, which is what we want, minus the position of particle Q at 0? Well, they already told us some of that. Remember, that position is negative 90. So if I plug that into my equation, I would have x of q of 2.8 minus negative 90, or that would turn into a plus 90. That is going to equal this integral. And again, we could just use the calculator to do this integral. And I'm not going to show you how to put it in the calculator again, but you should be able to do this. Again, that's already in your y1 function, so you're just going to do the integral from 0 to 2.8. When I plugged it in, I got 135.938 if I round. So that equals x of q at 2.8 plus 90. So I'm going to subtract 90 from both sides. So if I subtract 90 from 30, I get that the position of particle Q at 2.8 is 45.938. Okay, remember, that's not our answer. We're trying to find how far apart they are. Well, now I know what 40.75 is. Right, that's my first position. That's the position of particle P at that time. And now I know the position of particle Q at that time at 2.8. That says 2.8, even if you can't read my handwriting. So to find the distance between them, I just subtract the bigger from the smaller, which actually works out how I wrote it. So I'm just going to do 45.938 minus 40.75. And when I do that, I get that the distance is about 5.188. And remember, everything here was in meters, so I'm just going to say they are about that many meters apart. That is my answer for the distance between those two particles. All right, hope that all made sense. I know it's this is a pretty convoluted question, so you might want to go back and rewatch some parts and send me some emails if you have some more questions.